As you may be aware, I've been sick recently. I'm getting over it. But hey, the things you can do when you're sick. Though my body is constrained, yet my mind wanders. And what I've been doing is really experimenting with ray tracing. You may have seen in the past videos, I've been experimenting with different ways of getting memory physically from the CPU to the GPU like fast, and I feel like I've got that about optimal. The next stage I wanted to look at was acceleration structures. Now we had an acceleration structure and it was pretty good. As this thing upreses, you'll see that we are getting a full scene at what, close to 3000? It's always OBS, guys. It's OBS throwing the frame rate counter off, but it's up there. And you know, I always like to do this. So if we look up at the sky, we've got 5,000 frames per second. That's pretty good. But have a look. We've got 5,000 frames per second with few objects. And so clearly, here we have a frame drop. Clearly, the frame rate is sensitive to the acceleration structure. Now, at the moment, what we're doing is pretty much subdividing the space, picking the largest axis and just splitting right down the middle. And I mean, yeah, that's pretty good for this case, but there is a way to optimize it. It's called the surface area heuristic. The idea is that you have a box enclosing a bunch of spheres, and you take the surface area of the box multiplied by the number of spheres in that box, and that gives you a rough probability of a ray hitting the box. And the higher that number is, the worse, because you want to enclose the spheres as tightly as possible. So I had a look at that, and the next level, beyond simply picking the largest axis and splitting right down the middle, is to pick the largest axis, traverse, across the width of the axis, and progressively chop it into two boxes. Measure the surface area of the left box, measure the surface area of the right box, and compare those and just pick the box which minimizes the surface area heuristic. And we'll just give this a bit of time to res up. We should be able to see that there is a markable improvement. Now it's also deproved by, I keep saying this, look, we understand that, anyway, it's about 500 frames per second higher in my private tests. But what do we have here? Yeah, there's an improvement. I'm happy with that. This is a stable system. It's a little bit better than what I had before, which frankly was close to optimal already. There's one downside though. For this improvement, we've paid the price of a 53-second build time. That's not really acceptable. So what I then did is I looked at this and I said, okay, well, what are we doing? To determine the best split position, I'm actually testing all three axes, but as I noted in the previous section, we can just pick the largest axis and eliminate that from our degrees of freedom. Okay, so here I've basically done the same thing, except instead of testing all axes, I've just constricted it to the axis with the largest width, basically, of the box that I'm subdividing. And we can see that the frame rate is pretty much exactly the same. So, yep, the frame rate is the same, but the benefit that we pay for that increase is now it's taking us 19 seconds, which is a drastic improvement. But we can do better. So basically the situation is that we have a box. Imagine we have a box and we have 100 spheres in the box. We want to split the box into like 3 sections and test, each of those various. So like section A on the left, section BC on the right, then section AB on the left, section C on the right, and that's all I can think of. So another way we could do this is instead of saying, okay, we're doing section A, what's in section A? Okay, now we're doing section BC, what's in section BC? All right, now we're doing section AB. What's in section AB? Instead of doing that, because that's retesting everything, what we can do is at the start say, okay, we know which axis we're subdividing along, and we know how many slots we're going to basically split that into. Let's take, ahead of time, let's take all of the spheres, all of the objects, and work out roughly which of those boxes they're going to fit into. And then let's do, it's almost like a numerical integration, where we just sweep from left to right, and say, okay, if the left box is this size, then the right box has to be this size, and this is the cost. And then go, okay, now if the left box is a little bit bigger, what's that? And let's have a look at that. Okay, there we go. Let's give this a second. And we actually get, I don't know how this is possible, we actually get a further improvement on the frame rate. So that's nice. We're really squeezing blood out of the stone, as they say. But like I said, this is already close to the optimal case. These different types of acceleration structures are more important when we come to loading models where the geometry isn't uniformly distributed. But yeah, no, I'm really happy with that frame rate. And the build time, if you're interested, is about 3.1 seconds. So we've gone from like 52 seconds or something, down to 19 seconds, down to 3 seconds. I mean, how are we going to make this faster? They're almost... You're saying build it on the GPU. I know that. I'm thinking that too, but I'm just not masochistic enough to do it today, because what I did is I delved into the realms of data-oriented programming. Or I should say data-oriented design. Now, what is data-oriented design, you say? Well, previously we had classes, and classes held data. But now we don't have classes. Now imagine we've just got a big vector just of data. So it's just a NumPy array. So instead of individual, like this is sphere A, this is node B, and so on, you've just got a list of numbers. Oh, you're telling me it's all numbers? Always has been. So the way this is working, this is ugly. This is bad. There's got to be a better way to do it. But for now, I'm going to keep it suitably masochistic. But anyway, enough about that. The basic idea is we treat the data as if it's just a whole bunch of arrays, and it actually is. And the benefit of doing all this with NumPy arrays, you get a slight speed up with native NumPy arrays, but the real benefit of it is that we can compile the functions. So we have these nice compiled functions. I tried compiling all these functions and it crashed the computer. That's fine, but I think, fingers crossed, I think it's stable now. So, grand reveal. What has this little dark deal, this dark design, what has that done to my code? Well, performance is about the same. A little bit worse, I think, than the binning. Oh, man, who knows? It's so hard to... It fluctuates so much. Build time, well, let's try that again. There we go. Look at that. You see, that's so fast. Now, what happens is, because this is just in time compiling, the first time you run it, takes a bit to warm up. Second time, build time is 321 milliseconds. So we've gone from 3 seconds to 0.3 seconds. Let's try that again. Bam. Super fast. And that's still, 300 milliseconds. And that is still for a quality of I think it was 64 bins. I split this into, so that's doing it incredibly fast. Now, bit underwhelming today, because the obvious conclusion is, yes, we should be building this with a compute shader on the GPU, parallelizing what we can. There are some challenges involved in that. The big challenge is that I have to deal with shared memory. So let's say that I have 3,000 spheres, because I do have 3,000 spheres, and I've got a space that I'm dividing into 64 slots. Now, we don't want to go per slot, because then we're recalculating the spheres. The point is to take each of the spheres and say which slot do you fit into, send yourself there. But then, if I'm working on sphere A, sending it into slot B or something, sphere C might also be going into slot B, and then I have to synchronize operations, and it's just, for today, it's too much. So let's take our wins where we can. I've gone from 52 seconds down to 0.3 seconds for, as far as I can tell right now, this is about the optimal in terms of performance. We can probably improve the build time a little bit. We can definitely improve the build time. If you take one thing away from this video, apart from all my ranting and bad jokes, that thing is, when you're taking on a programming task, try to be aggressively optimistic. Try to be aggressively ambitious with cutting down the time. Anyway, have a great one, and I'll see you again soon. Bye.